Hello class, and welcome to our review of section 12.3, this one being Taylor polynomials at 0. So a Taylor polynomial, right? This is where exponential logarithmic functions can be approximated by a polynomial. This is called a Taylor polynomial, first developed by Brooke Taylor in 1715. So, the general idea of these Taylor polynomials of degree n. And this is when we have a function here, each of these derivatives being evaluated at x is equal to 0. But this is where we let f be a function that can be differentiated n times at 0. The Taylor polynomial of degree n for f at 0 is p sub n of x is, and we have this big, giant, long summation, right? F of 0 plus the first derivative of f at 0 divided by 1 factorial plus times x plus the second derivative of f at 0 divided by 2 factorial times x squared plus the third derivative of f at 0 divided by 3 factorial times x cubed. And this keeps going all the way down, adding them all up until we get to f, the nth derivative of f at 0 divided by n factorial times x to the nth power. And in shorthand notation, this is the sum from I 0 to n of the nth derivative of f at 0 divided by I factorial times x to the I power. And just to point out what these factorials mean, n factorial refers to n times n minus 1 times n minus 2. Keeps getting multiplied all the way down till we get to the value of 1, right? So something like 2 factorial, that's just 2 times 1, so 2. Something like 3 factorial is 3 times 2 times 1, which will bring a value of 6. So it's something of that nature. So as an example of this, right, I want to use a Taylor polynomial, so one of these large, lovely functions, of degree 5 to approximate e to the negative 0.2. So first thing that we need to do is to get this Taylor polynomial for e to the x. So how do we do that? Well, we know our function is originally, and I'll do that up here, is going to be e to the x. And we need to evaluate this at 0. E to the 0 gives us a lovely value of just 1. If we take the first derivative of this function at x, that's still e to the x. And the value of the function at the first derivative is, once again, e to the 0 or 1. And so the second derivative of f at x is still e to the x, and the value of the function is still 1 at the second derivative. And this keeps going on, right? So for the third derivative, I'll just put these ones in since they all make the same value anyway. The third derivative of f at 0 is 1. The fourth derivative of f at 0, 1. And the fifth. Since the derivative of e to the x is just e to the x, each and every single time. So the actual polynomial for this, before we write it for e to the negative 0.2, the general polynomial is f sub 5 of x, p sub 5 of x, is 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus 1 over 3 factorial, times x cubed plus 1 over 4 factorial times x to the 4th plus 1 over 5 factorial times x to the 5th. And we could put in the negative 0.2 here, since this was a negative 0.2. That's going to be in replacement of every single one of these x's. So P sub 5 of negative 0.2. This makes 1 plus, this is going to be 1 factorial. This gives us a value of 1. So this is going to be, actually I'll write with the factorials first. 1 plus 1 over 1 factorial times negative 0.2 plus 1 over 2 factorial times negative 0.2 squared plus 1 over 3 factorial times negative 0.2 cubed plus 1 over 4 factorial times negative 0.2 to the 4th plus 1 over 5 factorial times negative 0.2 to the 5th. And we can evaluate each of these, right? So this 1 factorial, let me use a different color just to make note of this. 1 factorial just gives us a value of 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is going to be 24. 5 factorial is going to be 120. But when we evaluate this entire thing with each of those factorials evaluated, this gives us an approximation of 0.8187307. And the actual value of this, if we just popped e to the negative 0.2 into a calculator, is 0.8187308. So it's only off by a couple of digits here at the end, right? If you look at the end values, it only differs with this being a 7 and this being an 8. So a pretty good estimate in that regard. So let me know if you have any questions or concerns. Thank you.